Hello, we will be introducing engineering economics in this course or this section, and we will have two separate videos to discuss engineering economics. The reason why it's really important to have a little bit of a discussion of engineering economics is none of the renewable energy projects will work at a long-term basis unless there is some engineering or some economic benefit to it. Now, that could be strictly from the perspective of reducing pollution. There could be some economic benefits. Hopefully, these projects actually can make it on their own in terms of just the baseline project, meaning that you can sell a kilowatt hour for less than competing technologies. Now, there is a lot of government support at this point, and renewable energies has gotten more and more penetration. A big reason is because of that. But also moving forward, they have to be able to do things on their own. And so one of the things to consider is if you're competing against traditional fossil fuel technologies, if you think about the timing, these projects have had 100 years or so of a leg up, if you will. So there's been a lot of effort in trying to get higher efficiencies, trying to figure out how to reduce costs. So there's been significant effort for that. Now, with renewables, the hope is that more research, better concepts, and better integration will actually improve the economics of renewables. But at this point, you do need a fair amount of subsidies to make renewables work. So we'll talk a little bit about how to come up with some cost of, or how to develop costs for projects. So we'll talk about time value of money, and that's one of the things that you listen to Einstein, that's one of the eighth wonders of the world, is how money will compound over time. It's not really magic, so that term is used in parentheses, but a lot of folks, especially younger college students, they miss the fact about how you can make money on your money. And so hopefully at the end of this lecture, you'll have a better understanding and appreciation of that. And you can make some decisions about how you do that. We'll talk about a discount rate, which is another way to say interest rate. It's just a little bit different perspective, but we'll use the term discount rate because that's more of a banking term, and it also changes your perspective slightly. And then we'll look at net present value, which pretty much tells you what it's looking at just by the title, NPV, net present value, which is the present value and the difference between competing options. We'll look at uniform cash flows, which you probably haven't been exposed to yet unless you've purchased a car or a home where you have some uniform cash flows to pay back the loan that you took out to purchase that thing. And then we'll look at the concept of equivalence, which, as most engineering students probably have experience with, you can essentially look at all different types of scenarios. And as long as the outcomes are the same, then we can use those baseline or either option, and we'll get the same exact result. So we talked a little bit about this. If it's renewable or not renewable, it has to be economically feasible to make the project work. And we've already discussed the different type of costs with any generating project. You've got fixed costs, the land, the taxes, the purchase of equipment, just the general maintenance of the generating facility. And then the variable costs tend to be primarily focused on the concept of buying fuel. And so depending on which renewable energy technology you use, for example, solar or wind, you do not actually have to pay for the quote unquote fuel. The fuel is free. It's the sun or the wind. And that is not owned by anybody, so you can get that for free. So variable costs on renewable energy projects tend to be much lower than other competing technologies. The fixed costs can be very different because depending on where you're building and how you're building, you can have pretty substantial fixed costs, particularly if you think about land, for example. And we'll learn more about this when we look at solar PV. The rule of thumb is you need about 4 acres of land to produce 1 megawatt rating. And if you think about, getting a 1,000 megawatt plant, you need a lot of acres, and that's much, much greater than most of the other facilities that you would do for comparison purposes. So you do have some pretty high land costs associated with it. You've already looked at fixed charge rate and then dollars or cents per kilowatt hour calculations. We did that when we discussed supply side economics. And I encourage you to review those to get a sense of what those terms are. And so now we're going to expand a little bit on that and do our application of engineering economics to really perform a very high level evaluation. Now, these are not detailed evaluations because you need a lot more risk involved. You need a lot of statistical modeling involved to kind of have a bunch of different boundaries, if you will, to include. But for the most part, it does give you a pretty good yes or no decision to at least proceed in further planning of a project. So what are our distributed resources? Distributed resources are essentially anything that can supply power over a period of time, and it tends to be non-centralized. So a large power plant like Maine Independent Station, that would be more of a central design because it's a 550 megawatt plant, and there isn't anywhere near the need for 550 megawatts in the VZ area. So that would be central because all the generation is divided amongst a very great distance, where distributed generation would be people's solar arrays on their house, for example, if they had a small wind turbine. And you can see the different technologies that would typically be found in distributed generation. Fuel cells, not that common in the US. You can have internal combustion engines. Those are not that common. Again, they're very expensive. Combustion turbines, if you are looking at sort of a larger facility that has a fair amount of load, you can go with a 1 to 5 megawatt, maybe even up to 10 megawatt combustion turbine. If you could do biomass cogeneration, so a lot of waste processing facilities, meaning you've got wastewater that you have to treat before you can recycle it essentially. And what happens is there's a lot of methane that's produced. And so in many cases, you can capture that methane instead of having to burn it off because it's a pretty bad greenhouse gas, the methane, you can actually burn it and it does still produce some CO2, but it doesn't have the same impact for greenhouse gas than the methane does. Small wind turbines, PV, and then any mini hydro. What are the resources? You can have better power factor because you can support power factor at those locations. You can increase the capacity of the grid. So one line, instead of having to provide 10 megawatts, maybe it can provide 5 megawatts because you've got 5 megawatts distributed throughout the line. That in turn decreases your losses because 10 megawatts flowing down the line is going to produce more power losses than 5 megawatts. And you can, really just simplify the amount of losses. And then you can also do stuff with demand side resources, which is not as common as it used to be. But demand side resources are based on, depending on the amount of load that you have, and more importantly, the amount of supply. So if it's a very warm day and supply is kind of tight, the dollars per megawatt hour are quite expensive. So if you can issue some sort of an edict, we need to reduce the load, you can actually have that automatically done. So maybe your heat pumps aren't running as hard. Maybe your lighting, you're turning off some lighting. Maybe you're moving some of the load to shift it to a different time. Maybe you're doing some absorption cooling, which is, again, not that common, but this is a way to sort of improve the use of the existing load without having to tax it so much. And so what do we pay for our electricity bills? So if you do pay for your own electricity, you're typically charged for two things in your bill. It's the energy charge, so it's the kilowatt hours per consumed, but even under there, there's a subset. So that actually has a generation charge, which is actually paying for the cost of generating it. But then there's also a distribution charge, which is in most of New England, we have deregulation. And so the generation is owned separately. So the utility will charge for both. They have to send a certain amount of the money that is on your bill to the ISOs, and then they distribute that to the generators. But then they also have to pay for the infrastructure to provide the energy to your particular home or facility. So that's the energy charge. If you are in different areas, they do offer a time of use, which means that during the day, when you have peak consumption, your power demands, your costs for energy tend to be much, much higher. So instead of doing things during the day, like drying your clothes, for example, perhaps you push it to start drying your clothes at 10 o'clock at night. There's less demand. So you have lower costs for generation, which means that you have lower you charge less to the customer. Now, that doesn't affect the distribution charge that we talked about previously, but it is a way if you're trying to save some money on bills that you can do that. I don't believe that that is available in the state of Maine because you need fancier metering for that, and you also have to have an awareness of it. Now, if you're a big facility, you can also have something that's called a demand charge, which the facility has to be able to, or the infrastructure that is for the utility system has to be able to supply the worst case demand for all the customers. And what they do is they can't predict with 100% certainty when you're going to need most of your power. So what they do if you're demanding a large load is they're going to charge you for a demand charge because they had to build the infrastructure to be able to support that load. And they don't do it at a specific time. They just figure out what is the highest power draw for a 15-minute time over the course of a month. And then that will be your charge that they'll charge $1 per kilowatt because, again, they have to pay for that uprated infrastructure that's not fully being realized to provide your power. And it is a minimum value that they're going to charge. And they can also do it on a ratcheting basis, which means if in June you were at, let's say you had a demand of, I don't know, 7 megawatts, and in August you went up to 9 megawatts, then your new demand charge is fixed at 9 megawatts. It may not necessarily go back down to the 7, so you might be stuck for a year at 9 megawatts. And so a lot of large users will spend a considerable amount of time trying to figure out how to reduce their demand because that's money that you're paying, but you don't really get a lot of benefit out of it because you're not getting the energy to do something useful. Another thing that larger loads have to consider is called power factor. So the reason why they charge for poor power factor is because if you do have poor power factor, you draw more current through the system, which in turn produces more losses. And so if your power factor is poor, you have greater losses than what they anticipated. And as a result, you have to pay for them. So they will charge you $1 per kVAR value. So again, there's a lot of work that's been done to reduce the power factor, or I should say improve the power factor to getting it above 0.9. You don't have to get to unity or 1, but 0.9 is usually sufficient for most utilities. So what about in the extreme cases? So this was on June 24th, 2025, which was a very hot day in all of New England. And I just highlighted Maine, but I actually included a map. I just happened to be monitoring the prices at that time. And this is what power costs were in the New England area. So you can see in Maine, 1,345. If you start going into Western Massachusetts, 1,070. In the Boston area, 1,079. So really high prices. Now, this doesn't necessarily tell you a lot of information, but the colors should also tell you a little bit about, hey, there's some bad things happening, orange and red here. But if you were to divide, and I just picked, Connecticut for price, $1, 1,063.82 equates to $1.06 per kilowatt hour. You probably pay around, this is just supply, you probably will pay 12 to 13 cents per kilowatt hour typically on your bill. So you're talking almost 1,000 times more than what they would pay. So what this translates to is very high cost for the utility, and they can't pass these down onto the users, at least when they incur these costs, because we have fixed rates that they have to go out, the utilities have to go out and petition the PUCs for a higher rate, and then they will get compensated. And so what they do is they have some space in their metering rate to go ahead and do that. But for the most part, this is just going to be tacked on to our next bill. And the reason why this was so high is their day ahead market. They thought the prices were going to be $500 a megawatt hour, but a couple of generators were not available for one reason or another. So those prices went out the window. And now you're pushing over $1 per kilowatt hour, which is extremely expensive. If you were to go to ISO New England's website now, and you were to look at their normal prices, it's probably $40 to $50 per megawatt hour, which translates to 4 to 5 cents per kilowatt hour. So are much more manageable as opposed to this particular day, real extreme prices. So let's look at very simple calculations. We're going to go ahead and look at simple payback. So how many years does it take to pay back an investment? This is a pretty simple calculation. We We don't really look at interest rate at this. We just very simplify it down dramatically. And if we take an investment and we divide by the annual savings, so we had to outlay some money, and we're going to get a certain annual savings per year, then this will tell us how many years it takes for us to pay back that investment. And your typical value for a payback is less than 5 years. Some investors will say 3, some will say 7, really depends on what you're proposing. But a general rule of thumb is you want to be paid back in 5 years, because 5 years is a lot of time. When you're making investments, the world can change, demand can change, you don't necessarily know. So putting your money out there for more than 5 years and hoping that you're going to pay back in that time frame is pretty dangerous. This does not include how long the system's going to last. So if it only lasts for 4 years, then this is a bad investment. If it lasts for 40 years, then this is probably a pretty good investment. And it fails to include that compounding value that we haven't looked at. So this is just a very dangerous one, but it does give you a very simple, hey, how long does it take to do this? And so if you want to do your initial rate of return, you can take 1 over the simple payback, or you can take the annual savings and divide by your investment, and then you get your initial rate of return. So let's take an example using simple payback. You have a 3 kW PV system. Its capacity factor is about 0.25, which, if you recall from our discussion on supply side economics, our capacity factor is what ratio of the facility is generating at 100%. So if you have a nameplate rating of 3 kilowatts and you ran it at 3 kilowatts for the entire year, day and night, you'd have a capacity factor of 1. Clearly, this has got to be less because the sun's not shining at night. So this is about a quarter. The system costs $1,500 to install, and the utility charges 18 cents per kilowatt hour. So we want to know what the simple payback is and what is the simple rate of return. So the first thing we need to do is figure out how many kilowatt hours per year we're producing, because we're paying for electricity on a kilowatt basis, and we want to do simple payback on an annual basis. So we end up with 6,570 kilowatt hours. We can figure out the savings because we don't have to purchase that much power. That's going to save us $1,182 per year. Now we take our $15,000 initial investment and divide that by our payback, or what we save per year, and it's just over 12.5 years. So is this a good investment? Well, we look at it from this perspective, probably not, because the likelihood of you, for example, doing it at your house, for example, and keeping it at your house for almost 13 years is not a great assumption. But if you convert it to a rate of return, you're looking at 7.9%, which is the return on your money. So that seems a little more worthwhile. But again, you really have to consider, what does this mean in terms of how long I'm going to be here? Because if you sell the project and it doesn't add any value to your home, then it doesn't really make a lot of sense. And so that's where you have to really think hard about these projects that have a very long time horizon. So money has 2 dimensions, right? Obviously, the amount of the money that you have, and then it's the amount of time you have that money invested or that you're going to borrow that money. And so the concept there becomes interest, right? Because let's say you're borrowing money. The lender has to lose the ability to use that money to do what they want. And they charge you a certain amount for the privilege of using their money. So that's the concept of interest. They have interest in that, and you have to pay them back that percentage or a certain percentage. Otherwise, it's not a good investment for them. It's similar if you put money into an investment. You could put it in a savings account. You could put it in a high yield savings account, put it in a CD. You could put it in the stock market. And the concept there is you're taking your money and it's no longer liquid, meaning it's no longer available to be readily spent. And as a result, I'm losing that ability to do something with my money. So I need to be compensated for that. Now, the level of compensation depends upon how long that money is tied up. So obviously in CD, I'm sorry, in a savings account, you can access that money whenever you need to. So the savings rate tend to be very low, or the interest rates tend to be low on that, because they can't make a long-term investment with that money and do something with it. They have to actually have a lot of money available in the event that you take it out. The longer the term is, the higher the interest rates are typically. So if you think of CDs, right, you're making a commitment to keep that money in for 6 months, 5 years, whatever term you select. And as a result, the bank will give you a higher interest rate typically. But in either case, you expect to be paid additional funds for the money that you have put in. So let's look at some compounding interest concepts here. So at the beginning of the year, I started at the beginning of the year and I put in $1,000. At the end of the year, if I'm getting a 5% interest rate, I've got $1,000 plus the 5% that is owed to me for losing or the access to that money. So that becomes $1,050. Then next year, I don't take the $50 additional that I put in, I leave it in there. And so now I'm getting an additional interest on the $50 that I made previously. So instead of gaining $50 like I did in the first year, in the second year, I'm gaining $52.50. I keep repeating the process until the end of year 4, I have $1,215.51. Where if I compared that to not compounding, if I was just getting the same $50 every year, I would be about $15.50 less than I would. So this is not a huge difference in terms of money, but if you think about it in terms of a percentage out of $200, you're talking 7.5% or so is what the effective interest rate equals once I include the compounding cost. So let's formalize that and just do the terms, but then we'll just do variables to see how it goes. And you can walk through this table. It's not a particularly difficult table to understand, but you can see at the beginning, I put in a P, which is a principal. The interest is the principal times the money that I make is the principal times the interest. And then I get that added to my principal, and that becomes my start of my next year. And then I walk all the way through, and after n periods, my amount that I have is my principal times 1 plus I, which I is the interest rate, times n, which is the number of periods. It doesn't have to be annually. It could be quarterly, it could be monthly, it could be daily, depending on what terms you've set up. But this is a quick way to find what your money will be in the future, given a certain amount of principal and interest and a time period. So we'll use that equation and formalize things. And this is a term, if you have taken some engineering economics, you may have seen some expressions this way. So our future value or our future worth is equal to our initial present worth or our original principal multiplied by 1 plus the interest times the number of years or the number of periods. You can rewrite that as just a generic term, which is F divided by P, which if you use engineering economics term, that is find an F given a P, find a future value given a present value, and then you have this multiple that you can calculate. So if we do our calculation here with $1,000 for now, our interest rate is 12 years and our period is 5 years, then what we end up with a future value. So this is out at the end of 5 years, $1,762.34. And those two are equivalent, meaning if I can get a 12% interest rate on the money that I'm about to lend to somebody or some organization, then if I have $1,000 today, or in the future, I have $1,762.34. Those are the same. There's no difference between the two. So if somebody asks you if you want to make an investment, and they'll give you $1,762.34, then you can do a quick calculation and see that your interest rate is 12%, which is a pretty good interest rate. So you may decide to move forward on this particular request. So how about checking for equivalency now? So we have $1,200 now, or you can get $1,500 5 years from now. So you're going to assume that the going interest rate today is 6%. So you can do two different approaches. You can find the future worth given the present. So our find an F given a P calculation results in 1.338. We multiply that by our current principal, and we end up with 1,605.87, which is greater than $1,500. The other way we can do it is instead of finding a future value, we can find a present value, which means we just invert the equation. And we divide $1,500 by 1.338, and we see that today's value of that $1,200 in $1,500 in 5 years is $1,120.88, which is less than the $1,200. So if somebody is asking you to make an investment in this, you might decline it, because what you could say is, I can get 6% interest rate by going to a bank, and you're offering me an interest rate that equates to less than 6%. So this would not be a good investment for you to make, because you're coming out in the black, if you will, compared to the two, in the red, compared to what you would be getting otherwise. And most of the time, it is better to calculate present worth than future worth, because in 5 years, having $1,500 or $1,606, it sounds like a good idea, but you really need to compare it to today, because if you're looking at $1,600, our impression is what that money is worth today. It's hard to envision what that money will look like in 5 years and how valuable that be. So it usually is easier to look at things and compare them to today, because that's our perspective. So this is sort of formalizing a term that you'll hear about a lot, but an interest rate is another way to say interest rate is called the discount rate. And so, as I mentioned, when you do things in present value, you're changing your perspective. So whether you look at things from an interest rate perspective, I'm getting 5% a year over the next 5 years. A discount rate is, I've got a certain amount of money in 5 years, and I have to reduce the amount of money, the value of that money, by whatever the discount rate is. And then that is going to tell me what my present value is. So it's the same term. It's just looking at it from finding a present value as opposed to finding a future value. So if I want to take a look at something that is going to save me $10,000 in 5 years, what is its present worth? What does it look like to me? So that $10,000 in 5 years, if I have a discount rate of 0.1 or 10%, it's going to look like about $6,200, not $10,000, but $6,200. If I can get a competing rate of 20%, now that 10K is only worth about $4,000. So it makes it way less valuable when you look at it from a present value using the discount rate. So the lower the discount rate, or the lower the interest rate, if you look at it from that perspective, then the higher the present worth. And so, meaning, if it's difficult for you to find competitive rates that are large, like we can see if we can only get a 10% interest rate or a discount rate, then its present value is going to be higher than with a lower discount rate. Because again, that $10,000 looks a lot less, because I can compete with other investments and make money. So we'll expand this into cash flows, and we'll start to see how we can break out present values, future values, and we can look at things in terms of annuity. And so the A stands for an annuity, which is basically an equal repayment over a course of time. It's the same thing if you have a car payment. You're paying a fixed, let's say it's $400 a month for the life of the loan. It doesn't go up, it doesn't go down, as long as your interest rate remains stable. So if you have a variable interest rate, that changes things. But if you have a fixed rate, your amount's not going to change. It's the same thing if you purchase a home. If you have that fixed interest rate, you're going to pay the same amount. Now, that only includes, for the case of a home, your principal and interest. You can have taxes in there, you're going to have insurance. Those can vary, but your actual payment is based on a fixed amount. So we have a cash flow diagram, which is shown on the lower right here, which shows inflows and outflows. So inflows are typically shown as an arrow pointing up, and outflows are shown as arrows pointing down. And then you specify the periods as shown with the number. So in time 0, I borrow some money. And over the next 4 periods, I spend a lot of money. I spend whatever money. Now, for an annuity, those arrows are all the same dimension. They don't have to be. You can do weighted cash flows. You can have some variable cash flows. It's much easier if you have fixed cash flows, so you can make some pretty easy calculations that way. All right, so if we want to find a future value given a bunch of annuities, and these actually can vary a little bit, so we can see that they have different values, we can go ahead and we can add all those up, and then go ahead and do our find a future value given a present value over the number of periods. So this is just a summation. Our future value is equal to the number of annuity payments we made. And then we have to go ahead and future value them based on the amount of periods or the number of periods they have until the end. And you sum those together, and then that will be your future value. Pretty obvious, pretty much makes sense. But let's formalize that a little bit. So if we were to go ahead and look at them individually, we can see that our first payment has 1 plus I to the n times our value. And then we work down until we actually have no interest rate that goes there. So you can have some different contributions just based on that time value that we've discussed so far. So let's go ahead and do a calculation here and figure out what the future worth of a bunch of different cash flows are and see what this looks like. So at year 0, I've lent out $2,000. And at year 2, I've lent out another $2,000. Whoever I've lent this money to promises at the end of year 3, they'll give me a $2,000 payment. And at the end of year 4, they'll give me a $4,000 payment. If I can get a discount rate or an interest rate of 12%, what should the payment be in year 5 so that I'll put up my $2,000 today and my $2,000 in year 2 so that I have, it's basically, it balances or matches what the investment would be for a getting a 12% interest rate return. So at year 0, I have my $2,000. So that's going to be a full time period. So that's the 1 at the end. So it's 2K times 1 plus 0.12 times 5. And then at year 2, now I've got 3 more years to go. So that is 2K times 1 plus 0.12 times 3. And then my positives here, my cash inflows, are the 4,000 I get at year 4 and the 2,000 I get at year 3. So when I do all those calculations, what I see is a positive $654.26. So I should expect to get an additional $654.26 of money to make this a valid investment. If this becomes a negative number, so if that was a negative 654, then I would actually have to pay the person out an additional $654 or not tell the person, and then I've got a better investment than the 12%. So this could be just one of those things where, if you want to evaluate something, you can go and do these quickly, and then you can make a determination. Hey, at the end of year 5, I want $1,000, I want $500. You can do a pretty reasonable calculation based on what we just. So we go back to this single payment compound amount factor. So this is just moving annuities to a future value. It's the find an F given a P. But now we can do something with a present worth value. So if we're finding a P given an F, we'll do this beta term, which is just for a single payment. So we're going to invert, and then we can see that we have 1 plus D, which is our discount rate, to the -1. Or if I'm bringing everything to a present value, I can just do however many periods I have, so that becomes minus to the n time. Whoops. So let's go ahead now and look at present value and future value for a cash flow. So we got at time period 0, no money. Then we get in $300. At the end of year 3, we put out $300. Then we get in $200. Then we get in $400, and then we get at year 8, we get $200. We get a discount rate of 6%. And so what you might want to look at is moving all this money to today. What is the present value? Is this a good investment? Or we can look at what the future value is and see, what money difference we would have there. So let's, whoops. So this is a little touchy. So the first thing we do is calculate the future value. And you can see the calculations over here. What we end up with is a future value of year 8 of positive $951.56. So that means that I should get an additional $951.56 for this particular project. If I do the same thing in a present value, Now I can see it is $597.04. And so to do this investment, what I should be willing to spend, or what I should be willing to outlay, is $597.04. That would mean it's equivalency. So that's essentially like having another payment at time zero. And so I don't have that. That would be the amount of money that I would outlay to basically break even on this investment. So that's where I would go ahead and do a calculation. And if I do for the discount rate of 6%, I can see that it matches by moving this 597 out to year 8. I get exactly the same amount, the 951.56. So that's just another way of checking to see if you get the results you're expecting. So it's pretty touchy here. So we can go ahead and do all our future valuing, and we can see that our present value, now we're using that beta term, which again is just 1 over, it's just P over F. And I can move all those terms over. So now I can present value the whole thing, and I can do a simple calculation. So I want to calculate the present value for an investment that returns 1,000 at the end of year 1 and 1,000 at 2,000 at the end of year 2. If I can get an interest rate or a discount rate of 10%, and that's where I can go to pretty much any competitive one, what I'll see is that my present value, by moving those two future values up to the present, I see that I can get $2,561.98. So that is how much I should be willing to invest. Anything more than that, then I'm better to go ahead and invest it in a competitive project. But in this one, if I go up to 2,500, let's say $62, then this is a reasonable investment for 10%. All right, so now let's compare different investments. And so we're going to look at the net present value, and we're going to compare just different investment types. And so what we see is our net present value, we should be willing to loan up to $2,561.98. But whoever is asking us to do this deal is telling us that they only want $2,400. So our net present value is $162. We actually have a positive. That is a positive number. And so we actually are making out $162 better than just taking that money and putting it into the bank. So this would be a decision that perhaps, yeah, let's go for it. We can make $162 over what the going rates are. So it's only a 2-year process. I make $162 over anything competitive. Let's go ahead and pull the plug and make this investment. So it really does. It allows you to compare two different investment strategies, or you can even compare multiple. You can compare hundreds of them, but you're looking for the highest net present value in most cases. Now, you are going to have some cases when that net present value is negative, and you may be that you have no choice. So the example I have here for a generating facility is you are required to invest in some sort of pollution controls to be compliant with new EPA regulations. And you're looking for the least costly option that meets the regulations and will give you the best bang for your buck. So if you're going to have a net present value that's negative, that means you're investing in something that you're going to lose money, but you're required to do it. Most of us don't want to invest in things that are negative, except if you have families, right? Those could be pretty expensive investments, but I'm kidding, those are obviously bring a lot of benefits otherwise. But if you're looking at pollution controls, yes, that is going to typically be a negative number. You're not going to be making money unless you can get some sort of carbon credits, and you can make money with carbon credits. So let's look at another example. We're going to take a look at a loan. So we want to see the net present value of the loan. So we will promise to pay back $1,000 at the end of year 1, $2,000 at the end of year 2, and $3,000 at the end of year 4. If the prevailing rate of where we can get competitive market is 8%, we want to calculate the present worth of that, so that we can decide if somebody's willing to do this deal, how much money should we expect to get? So we calculate our beta first, which is no big deal. I mean, you can just go ahead and invert it, or you can do the calculation any way you want. So our standard beta is 0.926. So at the end of year one, we have $1,000. We don't have to bring it back 1 year. At the end of year two, we have to come back 2 years. So we have to square that. And at the end of year three, our $4,000 has to be brought back 3 years. So when we sum those together, we get a present value of $5,815.93. So again, if you're asking the bank to loan you a certain amount of money, and they're saying, we want to get $6,000 or $7,000, we'll lend you $6,000, then go for it. You're actually getting a little bit more. But if they said, no, we're only going to be willing to lend you $5,000, then perhaps you've got to go to a different bank. So that makes a little bit more, it gives you items to consider when you're shopping around to do comparisons. So if we have uniform cash flows, our annuities are always the same, makes things very easy. We can calculate our present worth just by taking our annuity, which doesn't vary, and then we can just vary our beta rate based on, well, not our beta rate, but the multiple of betas that we have, and then we can bring that back all the way to time. So our present value is equal to A times the sum of our betas that are reflecting that. So beta should always be between 0 and 1, right? It's an interest rate, so it's not going to have a negative interest rate. So when you do the 1 over 1 plus D, it's always going to be 1 over a number that's greater than 1. So that number is always going to be there. So we can simplify this down and see that if we have an infinite set, we end up with 1 over 1 minus beta. And so we can simplify that equation to do 1 minus beta n over 1 minus beta. So we can expand that a little bit, and don't worry too much about the math here. What we're really focused is on the bottom is if we have an equal payment series that's going to go on for a very long period of time. And if that term might start, if that expression starts to ring a bell, that's our fixed charge rate, which is finding a present value, or I shouldn't say finding present value, given an annuity or how much you're paying every year, you can actually do the calculation over here. So that is, we're assuming a constant amount of annuities over the lifetime of a project. So we can use this expression over here, which is finding a present value given an annuity. So again, this is just the terms that we can expand. So we do it all in terms of our discount rate. You can see that all the end, and it just simplifies it down from there. So this is called our capital recovery factor, right? So that's just the present value. If you invert it, it becomes your fixed charge rate. And you can see that at the end, which it says the annual amount equals a present value, find an A given a P. That term, A given a P at the discount rate and a number of periods, that is in fact our fixed charge rate. So here is our uniform cash flows. We have a present value, we have a future value, and we have a capital recovery factor. If you use Excel at all of these automatic calculations are built in for you. You can actually use Excel to do this, which is where most people use it. In some cases, your calculator, especially if you have a business calculator, has a lot of these equations built in as well. So you can also look at that from that perspective. So let's compare cash flows for annuities. Like say you want to do 2 competing car loans, and somebody's offering you a certain rate or a certain payment over 6 years and another payment over 8 years, and you have a discount rate. So you can't just say, well, let's multiply the 2 together. Let's multiply them independently and see what it works out to be. That money that you're putting out in the future has to be discounted because for today, $500 today, or $500 in 10 years is worth less than $500 today. So we're going to go ahead and do a comparison here. So we have a cash flow set on the left, which is at the end of year 3, 4, 5, 6, 7. We're going to go ahead and put out $2,000. And we're going to compare that to at the end of year 2, $8,200.40, and our discount rate is 7%. We want to see if those are in fact equivalent to each other. So we're going to calculate the present value using our beta term. And we have to be careful here because we're only doing $2,000 in the case of the first example, the first system, from years 3 to 7. So we're going to bring those terms back during years 3 to 7, not years 0 and 1, but 3 to 7. Or in the last case, we just have to bring that back 2 years. It makes it a little bit simple. But in either case, they are equivalent to each other. So again, if you're comparing car loans from one dealer to another, you can pretty quickly do this calculation and say, what is my monthly payment? And then that's a little bit different because you're using monthly payments. So the end there would be monthly. So it would be, if it's a 2-year loan, it would be 24 as opposed to 2. But you can figure out, okay, how does that present value of purchasing that car from dealer A compare to purchasing a car from dealer B? They're giving me a longer term, a lower payment, and it does a really good job of helping you include those calculations in there, see what is the present value. So let's take a look at purchasing a motor. So this is another example we can use it to calculate if it's worth our while. So we want to buy 100 horsepower motors, and both of them will last about a 20-year period. We have a discount rate of 10%. The motors are both 100 horsepower, but motor B is a more efficient motor. It is a premium efficient motor. So to produce 100 horsepower of mechanical power, so that's the thing when you buy a motor, the 100 horsepower that's stamped on the nameplate is the mechanical ability to drive a load at a certain speed. The input power has to be based on efficiency. And so we're paying for kilowatt hours. So by getting a more efficient motor using 1.5 less kilowatt for over the life of the motor can be pretty significant. But let's see if it's actually worth our while to spend the extra $500. So we're going to operate the motor for 1,600 hours a year, right? Because we're not going to run the motor 24/7. We're going to run it, for, I don't know, what does that work out to be? 40 weeks at 40 hours a week. Our costs are pretty low because we're buying this directly from the transmission system, and we get a lot lower cost when you buy purchase from there than buying it through a distribution line. So we want to figure out which is the better deal. So now we're going to annuitize what the electricity costs are going to be for motor A and bring that value back to a present value over the life of the motor. So we have 2,400 plus, and we're bringing each one of those equal payments. We're going to assume that the cost for electricity does not go up per year, which again is a bit of an adjustment or a bit of an overstatement. If it actually increases, then we would save more money with motor B over the lifetime. But let's just make the calculation pretty easy. So we bring that back, and we end up with a cost of $86,000. Well, what we pay for electricity rates $86,089. We add that to the initial cost of the motor, and we get $88,489. We do the same thing for motor B, and clearly we see that the price, the amount we spend per year is less. In the previous example, we spent $10,112. Now we're spending $9,920. So about $200 less per year for electricity costs. But that becomes less and less important as we start getting further and further away. So let's go ahead and add our $2,900 to that. So we see that our more efficient motor over the lifetime costs $84,000 versus the $88,000. And then when we add that to our motor B, then we end up with $87,355. So when we compare and look at our net present value, we do 88,849 minus 87,343. Then there's a positive. We have to outlay $1,135 more for motor B than for motor A. So you actually save money for motor B, but it's not nearly as significant as one would think. If you did 20 years at $200, you're thinking, why isn't it about a $4,000 difference? Well, obviously we have to take out the $500 difference in the cost of the motor. But again, that $200 in 20 years seems like a lot less when we can get a 10% discount rate on our money. So your decision for this is probably purchase the less efficient motor. Again, unless you're really into, trying to maximize efficiency and you're trying to use that as a marketing tool, perhaps that, we really care about the environment. And so we're doing things at far reduced costs, then yes, you would go ahead and purchase motor B. But if you're trying to do things from a practical point of view, the likelihood that you'll never change that motor out over the 20-year life and it's going to run for 1,600 hours over that period is pretty small. Now, if you're building, let's say you're on the University of Maine campus and you're building a dorm room that are designed to last for 100 years, and you're going to provide heating and ventilation, and you've got a fan, and most fans are actually designed, or most motors are actually designed to operate for at least 20 years in typical operation, then yeah, that would be something that you would say, okay, we can save money there as long as the budget supports it. But if you're doing this for a typical industrial facility, the likelihood of you proceeding with motor B is pretty small. So again, it just gives you a perspective of, you can't just look at the yearly savings and make a decision. You have to expand that money over time. And to get a real sense of interest rates or discount rates, your best bet is to look at what the Fed rate charges and then add a couple points to that. That's typically a pretty good way to do a short-term one. If you're going to do longer term, 30 years out, you might have to add more than 1 or 2 percentage points to make that work. So, and that has a lot of variability too. So that's the other factor, is we're assuming a fixed interest rate over the course of 20 years. That is very unlikely to be fixed. It is often going to vary by quite a bit. And it really depends on a lot of the economics in our world. So if the times are good and inflation is running a little high, then perhaps the Fed will reduce or will increase the interest rate. Conversely, if the economy is stagnant and there is not a lot of jobs, then they'll drop that interest rate to, in some cases, they'll drop it to 0. And again, that is spurring people to borrow money to actually start to build things and to go from there. And so the whole concept is based on, monetary policy to keep jobs and inflation at certain levels. So that's all I had for this particular video. I hope that you found it fascinating and you have a pretty good perspective of what the economics of things look like. We'll expand more and we'll start to include the effects of inflation in the follow-on lecture. So I hope you have a wonderful day, and I look forward to our next lecture. Take care.